other responsibilities. I won't go through details, but I wanted to say that his focus is on, he's known for that convex optimization, and he wrote many technical papers that you can find on his website. He has an unbelievable website, and what is the most impressive, that on the average, 1.3 million people visit per year his webpage. So I encourage you to look and see papers and other stuff that you will find helpful in your research and also in teaching. And speaking about recognitions, he has been recognized very highly. Some of awards, and he got many awards, but some of them are stand-up. IFAC Fellow, the highest grade in profession in IEEE, and also personally, I am on the board of American Automatic Control Council, and getting award, Ragazzini Award for Education, for teaching is something. So for me, personally, this is one of the most competitive awards. So he has honorary doctor from Sweden, and so many. But on personal note, let me tell you, when I organize workshops for high school students and high school teachers in the United States, Professor Boyd was one of the keynote speakers in 2002, and it was the most inspirational for teachers lecture. So I hope that this lecture will be most inspirational for each of you and for all of us. Professor Stephen Boyd. Please you get here.
Projector on?
1 minute.
Okay. So, well, while we're waiting for the projector to wake up, I should say, first of all, I'm honored to be here. I'm very happy to be here for many reasons. So I'm very interested in control education and education more generally. And I'm also very happy to be here at a place and a time which has a special connection to Lyapunov, which has had a lot to do with the kind of work I've done. And so that's, this may be a good time for me to say. In my talk, I am going to do terrible things with Russian names. And you probably won't recognize them. And I'm apologizing now. So, for example, we put in the US, when we talk about Lyapunov, we say Lyapunov. And so I decided in the end, it's easier for me just to keep the American pronunciation. And you'll just have to translate yourself. Okay. I should also say a few other things. This talk is actually going to be a talk about ideas. So not about, unfortunately, you won't see any nice videos of experiments. But it's going to be a talk about ideas, and actually specifically the ideas of Lyapunov. And how they go together. They're still going very strong 120 years later. And I will, along the way, get to say things about what this has to do with education and how this is important for education. Okay, so what I'm going to do, again, it's just to talk about the ideas. Now I'm going to follow the history of the ideas. And I'm going to start by even something that goes back before Lyapunov. And we'll look at the idea of it's a precursor to his ideas. And we'll look at the idea of conserved and dissipated quantities. Then I'll say a little bit about his methods. Now I think everyone here knows about the standard Lyapunov methods. Instead, I'm gonna focus on different aspects of it. So I won't be repeating the same things you've seen or learned or taught. I'll be talking about how it's actually a much wider idea than most people recognize. Then I'll come to the main point. And the main point is going to be how convex optimization, when connected with the ideas of Lyapunov, you get something that is incredibly powerful. And in fact, it's something that empowers students. So we'll see how this works. You'll see little bits and pieces of this. And that's the connection it's my belief that this is actually how control should be taught. We'll look at two examples just to see how this works. One is on worst case performance. Another one is from stochastic control. And this is something I've been working on literally this year. So 120 years from the 1892, which was when the thesis on the stability of motion was finished. And then I'll just finish up with some conclusions, although along the way, I'll make various comments about various things, and especially about teaching. Okay, so we'll start with the idea. This is the precursor. So this is mid-19th century. So you have a dynamical system, that's x dot equals f of x, and I have some scalar valued function v on Rn, and it's a conserved quantity, and this has many other names, integral of the motion or an invariant. If along every trajectory of this system, it's a constant. And what that means, of course, is that it's time derivative, which you can write this way. It's the gradient of v, and the inner product of that with the vector field, if that is 0 for all x. Okay, so this is, everyone knows this. This is, this is 200 years old. Okay, now classical examples would be things like this. The total energy of a lossless mechanical system, the kinetic plus the potential energy, is constant because there's no mechanism for loss. Something like this, the total angular momentum of a system about an axis, something like that. Or you have a system with a fluid that moves around a compartmental system, and the total fluid will be constant, even though in any particular compartment it's changing. And the idea here is, in this case, the trajectories will stay in the level sets of v, the sets where, so for example, if you have planetary motion, the configuration will move along these surfaces, algebraic surfaces, where, for example, the total energy is constant. Okay? So again, this is just a precursor. Well, a dissipated quantity is this. If this function, scalar valued function, is decreasing, that's a dissipated quantity. And dissipated, of course, refers specifically in English to energy. But here the idea is we're going to make it more general. So if you simply have any function and it decreases. So here we've gone, and this is very important because this is going to be a theme, that you go from an equality here to an inequality. And this gives you a dissipated quantity. So that's a dissipated quantity. If it's decreasing, and the examples would be something like this. The total energy in a system with loss. So if you have damping or something like that in a mechanical system, then what happens is the potential plus the kinetic energy, the time derivative, is exactly equal to the negative loss, right? The dissipation. And in this case, the trajectories stay in the sublevel sets. That's the set of points where this function is less than some number. Okay, so that is that's the idea of this. And we're already getting to a hint of the Lyapunov idea, and that's this. If these sublevel sets are bounded, and if the trajectories stay in them, then that tells you the trajectories are bounded. And now it's time for 1892. And we get to the idea of Lyapunov. And it's actually, these days, I guess if you teach it, I teach it, you don't stop to think, actually, of how radical the idea is. You just teach it because, well, I teach it because I learned it, right? But in fact, it's good to go back and think about it, and to actually think about how radical this idea was. And it's actually very simple. And it's basically this. In all the examples I showed you so far of a conserved quantity, of a dissipated quantity, all of these ideas come from physics. V, you don't find V. V exists. It's the total energy. It's the mechanical plus the potential energy. It's the angular momentum. And it's conserved, or it dissipates, right? So the idea here essentially is this. This function doesn't have to come from physics. In other words, instead of it being given to you, you can actually make it up. So this is, and if you think about it, this is not obvious. This is it's a brilliant idea. And in fact, you can then take it one step further. And you'd say, instead of simply observing that the total energy in the system is decreasing, that's what a physicist would do. Instead of that, we'll say instead, you know what, let's find a V that establishes some property you'd like to know. It turns everything around. V goes from something that you describe to something that you proscribe. In other words, you figure out what it should be. And the idea then, of course, is to use this function, traditionally called the Lyapunov function, to establish a property of trajectories. And I should say, that's even the case when you can't write down the trajectory, when you can't actually write down a formula for the trajectories. And of course, if you know about this material, it's not even, it's actually especially when. Because that's really the point, is to be able to say something qualitative, and we'll see, by the way, very soon, quantitative, about the trajectories of a system, even when you cannot write down the equations, the actual solutions, right? So this is the idea. And the classic example of it is this. If you can find a function, v, with bounded sublevel sets, and v dot less than or equal to 0, then all trajectories are bounded. And this looks very much like the observation from before. It looks the same, except this is quite different, because here we're saying, if you can find such a function, right? So it's not, this is not physics. Okay, now, of course, everyone knows all this. But actually, one of the points I want to make today, and it's why I believe that in teaching control, I think actually Lyapunov's ideas should be actually at the center of teaching control. That's what I would do. I would teach everything from it. It's not just stability. We hear about it, we teach about stability. It is far more applicable than just stability. And in fact, the truth is stability, as a practical matter, is completely meaningless and useless. Right? No one cares if something is stable. It has no practical consequences. It's completely right? It's unacceptable. What you want to know quantitative things, like if I move the state around, how long will it take to move back to some stable point or some set that's invariant? These are the things you want, quantitative information. And in fact, Lyapunov's methods do this. So for example, it's not just stability. You could do things like estimate or bound performance indices, right? So this is interesting. Now it becomes actually very useful and not just something that is theoretical. You can do things like bound or estimate decaying growth rates, or what's now known as the Lyapunov exponent. You can handle things like uncertain dynamics and stochastic systems. We'll see an example. Actually, we'll see an example of each of these later. You can handle things like time delay systems, reachability. So when you have an input and you ask, what states can you get to? So these are the types of things you can analyze using the ideas, if not exactly the methods from 1892. Not the methods from 1892, but the ideas certainly. You can do things involving input and output analysis. You can analyze things like passivity or bound gains. It turns out you can also use it for things like state feedback synthesis and stochastic control. And I will give an example of this. But in each case, what it comes down to is this. You need to find a function, a Lyapunov function, v. It has to satisfy some properties or optimize a bound. You might ask, where does it optimize it? Or why do you optimize a bound? Because what will happen is we'll come up with a condition which gives you a bound on, say, a performance index, an upper bound. If it's an upper bound, then the obvious thing to do is to minimize the upper bound over v. That would give you the best upper bound you can produce using this method, right? So, and we'll see that's going to be a theme. So from now on, I will never speak of stability again, because I personally think it's completely uninteresting and useless. Well, it's, okay, if the system is not stable, well, it depends what it is, but if it's not stable, it's not going to work as, for example, a control system, right? But I think the correct way to describe instability is to simply say the control system doesn't work. That's actually the correct statement. Okay, so big question is how do you find a Lyapunov function, and also we'll see another interesting question: how do you verify its properties? And so we'll see what this is. The first is We'll start with something simple. Now for linear dynamics and quadratic cost, there are generally speaking analytical methods, actually. Even no matter what you're doing, there are analytical methods for these, for analyzing stability, decay rate, all of these types of things. And here, the Lyapunov functions you're looking for typically are quadratic. And in fact, in the simplest case, they can be found by solving linear equations, right? And that means this essentially, from 1892. It meant that in the language and ideas of 1892, there was an effective computational procedure. In other words, you solve linear equations. That's 1892. One thing has changed since then. We'll see, all we're going to do is generalize the idea of what is an effective computational method. And instead of just solving linear equations, we're going to solve convex optimization problems. So that's actually the entire talk. That's it. Okay? So, okay. Now, in these cases, for linear dynamics and quadratic cost, that's all very classical, and they're typically sharp. And what that means is that the bound you get is typically exactly the number. If there's a performance index, you can get an upper bound, will go all the way down to that number. If it's a lower bound, it goes all the way up to that number. If it's a binary condition like stability, it will be if and only if. Okay? It will be necessary and sufficient. So that's what I mean by sharp. Okay. So, of course, we're not that interested in solving this problem for linear systems and quadratic cost because these systems are fairly simple. The idea is that we want to do this for things that are not linear or something like that, or have uncertainties or something like that. And so there are some traditional sources for finding a Lyapunov function. Okay, so one is physics. And of course that's kind of funny because the essence of the idea is that your function does not have to be from physics, but here you go and you find out that one of the most fruitful places for it is in fact sources for these is physics, right? So that's one. It could be this. It could be the exact Lyapunov function for a related linear system, and that describes all of Lyapunov's works. His first theorem, his second, and his third. That's all this form. In other words, you take a system, you're an equilibrium point. You take the associated linear system, you solve that Lyapunov equation exactly, and then that's the one you use. So this is from 1892. If you move forward to the 40s, 50s, and 60s, in fact, all of these methods, like the circle criterion, Popov criterion, these are graphical methods. And in fact, it was shown, I don't know, maybe in the 70s, 80s, something like that it turns out these graphical methods are absolutely nothing more than a method for constructing a quadratic Lyapunov function. Okay, so it turns out, so what this says, in fact, there are almost all stability type results that I know of actually either are directly related to Lyapunov's ideas, or even if they look very different, something like the Popov criterion, it's a graphical criterion, are intimately related to these ideas. Okay, so how do you find a V? Well, let's go back to 1892. So here's how he did it. You choose a form of V. For example, you say, I'll look at quadratic. And this is called a Lyapunov function candidate. It's a candidate because it's not a Lyapunov function until you can establish the properties that it has to satisfy. Okay? Then what you do is you find values of the parameters for which the required properties hold. And this is done up until maybe 1940 or so by hand. I mean pencil and paper and arguing and just using basic mathematics and inequalities, algebra. That's what it was. Okay? Now, of course, what that meant was it was limited to second order systems, third order, maybe fourth order, but with a lot of trouble, right? So this is the idea. On the other hand, it's still quite spectacular what you get. All right, let's go to the other end and let's look now. So the modern approach, and I would say this is from the 90s or something like that, and the last decade. And so the modern approach is this. You choose a linearly parameterized Lyapunov function candidate, like quadratic. And so you say, I'm going to look at quadratic functions. Then what you do is you find values of the parameters that give you the Lyapunov functions, for which the required properties hold, and using convex optimization. That's numerical. right? So this is going to be the modern approach. Okay. Now this traces to maybe the clearest statement of this, or maybe the first entirely clear statement that this is how it should be done is from Piatnitsky and Skordinsky. Okay? So that's maybe the early 80s. Okay? So that was an early one. Although I think many other people knew about this idea. It certainly, no one would say this is like a radical idea. So this is the modern approach. And here's my claim. If we could resurrect Lyapunov and explain how we apply his method now, actually we would explain two things. Number one, we can use your method to do much more than just certify stability. Much more. We can do things like, we can synthesize controllers. We can bound performance. He would understand it. Okay? And if we said there's one other different thing, and only one other different thing, and the other different thing is this, we search for Lyapunov functions using convex optimization. He would of course say, what's that? I would explain it, and he would say, that's great. I claim that this is the idea. So my claim is that he would approve. Now, he would probably not, at first he would be uncomfortable because he's from the pencil and paper crowd, you know, the 19th century mathematics tradition. But after a while, he would get comfortable with it and embrace it. So that's my claim. Okay. So how do you find a Lyapunov function via convex optimization? Well, I'll give you some rough ideas. This is a huge field, so I'm only going to give you just a broad picture and ideas of how this works, but it's a huge field. Well, let's take quadratic. So, if you have a quadratic here, many of these properties turn out to be matrix inequalities involving P. Like, for example, P is positive semi-definite, or P is positive definite. That's an example. Now, all of those inequalities, they're convex in the parameter P. Now, a matrix P, which is symmetric, and of size n by n, has n times n plus 1 over 2 entries in it. Right? So for n equals 10, this is already like 55 points. For n equals 100, this is already quite a lot of parameters. It's way beyond anything that can be done by hand. Right? So that's the important part here. So it says that searching to find over P, that's a convex optimization problem. Right? And the way we think nowadays is you'd say, well, it's a convex optimization problem, therefore it's readily solved numerically. Yeah. Now, this is, there should be a little asterisk here saying something like usually, or mostly, or except for some possible numerical errors, or something like that. But generally speaking, this is at the highest level, this is a sort of a correct statement. Okay. I'm not going to talk about these more sophisticated methods, but all of the follow-on methods that follow in this arc of ideas from 1892 to 2012, all of them fit this model, every single one of these ideas. So there's the S procedure, and this was introduced by various people like Lurie in the, this is the 40s, maybe 50s, something like that. What it comes down to verifying that a quadratic inequality holds on a set defined by quadratic inequalities. And the S procedure, it's a very simple condition. It's like duality, but it turns out it's extremely powerful. And it's in fact the root of many modern methods from the 60s, 70s, 80s, 90s. Last year, this year, can be traced to nothing but S procedure plus Lyapunov's methods. That's it. Even when it doesn't look anything like it. So, you want an example? How about this? All of robust control, pretty much. Right? I mean, a few exceptions, but most of robust control is Lyapunov's idea, S procedure, convex optimization, period. Okay? So, okay. Now another method, I'm not going to say anything more about this, because either you've seen this and know about it, or you don't, and I won't be able to explain it here. Another modern twist is the idea of sum of squares. And the idea here is that you would use higher order polynomial Lyapunov function candidates like quartics instead of quadratics, right? This is actually much more complicated. And immediately you ask the following question, something like, when is a quartic non-negative, right? it's not obvious, right? It turns out there are completely effective methods for this. It reduces to semi-definite programming. It's convex optimization, okay? So these all reduce to convex optimization problems, right? So, yeah, by the way, I don't think there's a big deal about this. You could do the same thing you could talk about solving linear equations, or you could talk about the singular value decomposition, or you could talk about the eigenvalue decomposition. These are effective, these are methods where you learn, the theory, there are effective algorithms, there are effective implementations of the algorithms, and eventually it just seeps in and it becomes part of the background culture. It becomes something that students should know about, right? These days you would never say a student does not need to know about singular value decomposition. You would never say that. But 30 years ago, you would. 30 years ago, singular value decomposition, maybe 40, was considered an advanced topic. But now it's not. Now everyone needs to know it. So my claim is, this will be like linear algebra and eigenvalue decomposition. Everyone needs to know this, in my opinion. Okay, so I'll do a quick overview of convex optimization. It will be a very quick overview. I'm going to focus on some stuff that's new. Okay, now the classical form is this. You minimize an objective function subject to some constraints, inequality constraints, and some equality constraints. The equality constraints must be linear. And the constraint functions and the objective function are convex, so they have upward curvature. They curve up like this. Okay? And so that's this inequality, and I think everyone knows about this. Okay. Now the more modern form is something like this. You minimize a linear function subject to the variable is in a cone and a linear equality constraint. And this is supposed to make it a generalization of linear programming. So if this cone is simply the non-negative ortho, this is a linear program here. So on the other hand, if you take it to be something like a Lorentz cone or a product of Lorentz cones, you get a second order cone program. And if you make this positive semi-definite matrices, you get an SDP, right? In which case, now these are all convex optimization problems, right? That's kind of like the modern standard form. Now why would you study this? Or more importantly, maybe for those who are now teaching, why would you teach this, right? And here are the reasons. This is a very, it's a very truncated list. The reasons are these. First of all, there's a beautiful and nearly complete theory, and it's absolutely beautiful. You can talk about duality, which is an organized way to create balance on things. The optimality conditions are usually very nearly necessary and sufficient. They're sharp. So just the theory alone is beautiful. But maybe more important is this. There are effective algorithms and methods, and that's in theory and practice, right? So there are methods that get you the global solution, not a local solution. And they give you an optimality certificate, right? So it's not just that here's the solution, but you get a solution and you get an independent verification that that solution is optimal. Right? So that's a luxury, by the way, in numerical computing. Right? In numerical computing, you usually get an answer. You have to, well, I guess that's not true. You can check some things, right? If you solve linear equations, you can look at the residual. Okay. And these methods have polynomial complexity, but I think probably more important is that they work very well in practice. In my opinion, that's far more important than the polynomial complexity. Another reason to teach it, and I think this is extremely important, is you get conceptual unification of many methods, right? This is, I actually think that's important. Because I guess if you teach, there's two ways to teach roughly, here are the extremes. One is to go in and say, oh, here's this method and that method and this method and that method, and last Wednesday we did this method, and here's another method, and here's this method, and here's that method. And I can promise you in that case the students will learn nothing at all, right? The right way to do it is to come in and say, actually, you will know there are actually hundreds of different named methods. They all look very different. But in fact, there's only 2 or 3 ideas involved here, and here's what they are. This students will understand, right? So and I think this allows you to unify all sorts of things, right? And to say, here's how it works in machine learning, here's how it works in statistics, here's how it works in control. And it's very nice to see all of these things tied together. But the real reason I think that this should be taught is this. There are just tons of applications, right? Tons. So I think this is the real motivation. Okay, so what are the application areas? And again, if you may know this or not, but I'll just go over some of them. So machine learning and statistics, they're essentially almost all of the methods that are actually used are based on convex optimization. They may not be relevant because these are huge scale problems with 100 billion variables. And they're not solved using any of the standard methods or anything like that. They're solved using custom methods that they've made up, like stochastic gradient type thing. And methods that run on huge data centers and things like that. Nevertheless, almost all of them are convex optimization problems. And the only other thing they would use would be something related to principal components analysis and SVD. That would be it. Finance. So a huge number of problems in finance are convex. A huge number. Much of supply chain, revenue management, modern advertising. These are all that. It comes up in signal and image processing and vision, networking, circuit design, strangely enough. Actually, both analog circuit design, digital circuit design, and everything in between. Combinatorial optimization, that's very strange because in some sense, convex optimization problems are easy. Combinatorial optimization problems are hard. But the most effective methods in combinatorial optimization rely on convex optimization as a subroutine. Areas like quantum mechanics. And of course, our interest, which is control. Right? So by the way, this is maybe a good time for me to say something about teaching. I teach a course on convex optimization, and it is a lot of fun for many reasons. But one is that you get students, I get students every year from 20 different departments. So from math, from pure math, applied math, statistics, computer science, mechanical engineering, aerospace engineering. I get people from genetics, I get people from economics, finance. It just goes on and on. And it's actually a lot of fun for them because they meet each other. And it's a common meeting ground for people who do modern applied mathematics, right? So it's a great place for people to, well, just to find out there's other people doing not exactly what you're doing, but using the same ideas. So you have someone from genetics talking to someone who's doing graphics, talking to someone from the business school who does finance. And they get to see that although what they actually do is quite different, the methods are similar, right? So I think from a teaching point of view, it's a lot of fun. It's fun for me, and it's also fun for the students. Okay, let me say a little bit about the history. Well, first of all, the mathematical basis is about 100 years old. Actually, very interestingly, I think it's even the same year that actually the ideas were around in the mid-19th century. But it got named by Jensen, actually right around the same time, turn of the last century. So around 1900. So convex analysis was very well developed already by 1970. So by 1970, it was very well developed as a mathematical field. But I think focusing on the computational aspects and the algorithmic aspects, I would say that the big events would be something like the simplex method for LPs. And that has a Russia, Stanford connection there, that this was Kantorovich and Danzig at Stanford. And in fact, the year is probably earlier than this, but it doesn't matter. So, all right. Now the next big event, I would say, would be in the 60s, I guess, in Kiev, right? So this is Shor, in the development of subgradient type methods, right? So this would be the next big event. Right? This is very important because what it showed was that, I mean, conceptually, this is a huge advance to say that there are algorithms that look like gradient methods, but they apply to non-differentiable convex functions. That's actually a big step, and it's a very interesting one. And you could give a whole talk on that too, by the way, on the history of that idea. The next, I would say, big advance is in the 80s, something like that, although I can say a little bit about that, and that's from Nemirovsky and Nesterov Nemirovsky, and that's the development of interior point methods, right? So, and other names you'd hear associated with this would be Karmakar, sort of in the West. That's for linear programming. But then it turned out, actually, when people went back and looked at the history, it turned out that there was this guy, Deakin, who developed essentially all of it, I believe, in the 60s, and was completely ignored in the Soviet Union. and completely unknown outside the Soviet Union. But it was all there, almost all there. Okay, so, and which just goes to show you when someone comes to you and says, this is new, you should not trust that, right? Because it's very likely that somebody knew this some other time. Or actually, my advisor when I was in math said that it's presumptuous to think that you would ever know anything that Gauss didn't know, right? So we used to joke about it. So, all right. So I'll talk a little bit about this. High-level languages for convex optimization. Now this is in fact relatively new, although like everything else, you can trace it back to the ideas, go back to the 60s and 70s. Okay, so what do these look like? And by the way, what I'm about to show you is what makes the ideas I've shown you so far, which are, you would have to say, very theoretical. The stuff I've shown you so far is not something I would teach undergraduates. But I'm going to show you what would allow me to teach this to undergraduates. And now you'll see. This is the innovation that allows that. The idea is you have high-level language support for convex optimization. So you describe a problem in a high-level language using the rules. I mean, there are mathematical rules that you must obey, but if you obey them, it will work. And then this description is automatically transformed to a cone problem, and then solved by a solver and transformed back. So let me just show you what this looks like, or what the idea is. Actually, first let me tell you what the implication of this is. The first is, it enables you to do extremely rapid prototyping by writing a short script. So you want to solve a convex optimization problem, and it's not huge, it doesn't have a billion variables. If it's a modest problem, I can write a 15-line script and solve it. I can write scripts in 1 minute, 2 minutes. These are homework exercises for students, right? It means that instead of being passive and listening to somebody lecture about Lyapunov methods and V dot and this, that, and the other thing, and the S procedure, the students get to actually not just hear about or write with pencil and paper something like S procedure or whatever. Instead of, what it means is the theory is now actionable. It actually allows students to do things. You can solve problems, you can get numbers. And this does two things. Number one, it makes it practical, and number two, the implications for teaching is absolutely enormous. It means you can have undergraduates doing this. I do. I get undergraduates in my classes, and they're just fine. I mean, the bottom line is you write a short script, and you can do a lot. It's quite impressive. Let's look at an example. This example is CVX. As developed by a former student of mine and me, and maybe around 2000, although, again, you could trace the ideas back much, much earlier. So let's look at a problem here. This is one that would come up in machine learning, and I just made it up. It's just a made-up problem. It says minimize a 2 norm of ax minus b plus lambda is positive, times, so this is L1 regularization. Oh, subject to some constraint that this is interpreted element-wise. So all entries of a vector are bigger than -1, right? So this is that's the problem, okay? So, and I'll tell you how this worked before CVX. Before CVX, I would be in my office. We would, my students and I would look at this, and we'd say, yes, that's how we want to do image denoising. We'd make up something, and it would have this form. At which point I would leave, I would go home, and the students would then struggle and write pages and pages of code, debug it, and things like that to solve this problem. Because we could look at that and say, that is a second-order cone program. There are second-order cone program solvers available. So I would come in feeling fine the next morning, and the students will have worked all night, and I would say, how did the image, how did the image de-blurring method work? And they'd say, not so well. And I'd say, oh well, right? So today, to solve that problem, you type this into CVX. Nothing, absolutely nothing more. And the point, this is just completely executable code. And the idea here is that the gap between what you code and the mathematics is very small. In fact, frankly, this is clearer than that, right? Because you formally declare what are variables and so on. Okay? So, by the way, this is another very important thing I think in teaching, is embracing computation. A lot of people talk about, for simulations and things like that. I actually think it's much deeper than that. I think actually that it will affect the mathematics, right? So what I mean by that is that modern computation will actually support very sophisticated calculations. Not just numerical simulations of how a 6-degree of freedom system operates with some control system, or how an airplane lands with a crosswind and something like that, and some control system operating. That's very important too. But here what it means is that very high-level things, like a convex optimization problem, you can actually, you can use the computer power not to solve, but in fact to do the analysis. In this case, what has to be checked here is whether or not this is a convex problem, and if so, how to transform it back. Okay. You know what? It's colored here, and it's black. You're missing red, I think, but that's okay. So we have 2 of the 3 colors. I'll try that. Okay. Now we're going to look at 2 examples, just to see how does all this really look. These are just the ideas. Let's see what they really look like. So here's an example. So this example is this. They're very simple ones because I have to produce examples that fit on one slide, the ideas. So here it is. I have a time-varying linear dynamical system, so that looks like this. And this matrix A can actually be any of k different values, right? And in fact, we'll see later that whatever works here will actually work if A is in the convex hull of these. Okay? And we have a quadratic sum performance index. It's this thing. By the way, this could well be plus infinity. That's possible. Okay? And what we want to do is we give the initial state, and we want to find what is the largest possible value this can have for this time-varying system. And what that means is choose a sequence of A's that makes J as large as possible. Well, if you like, it's an optimal control problem. Except the choice is you choose the dynamics, and instead of minimizing a cost function, you're maximizing. But nevertheless, that's what it is. Okay. Now, of course, when k is 1, it's just a single linear system, and there is actually then, of course, we understand exactly how to do it, and you solve actually a Lyapunov equation from 1892. That's this. So you solve this equation. That's a linear equation for p. You solve this, and if the matrix P has a negative eigenvalue, then J is plus infinity. If not, then x0 transpose px0 gives you the value of J. And now this is, you always start with the simple case, that's this, right? And in fact, a theme in Lyapunov's ideas is that what happens is you relax an equality to an inequality, and something happens. Okay? So let's see what that is. Here's a Lyapunov performance bound. By the way, here's an example, a very simple example of Lyapunov's ideas applied to something well beyond stability. Now I'm estimating a number, a performance metric. By the way, plus infinity means it's unstable. Finite implies it's stable. So, okay. But here we're going to get the actual number. We're going to get a number for it. Suppose you have a function that's non-negative and satisfies this, that whenever you operate by one of these matrices on a point x, then V is less than the previous V by at least x transpose qx. That's the stage cost. So in this case, that tells you that the value of this function at each next point is less than or equal to the value of current minus this thing, and you rearrange this and you get this sum here. Now this thing here is we can remove this because this thing is non-negative. And then of course that says that t can go to infinity, and it tells you that if you can find a function that satisfies this, then the worst case objective is less than or equal to v of x0. Okay, so that's the idea. And it's again, it's a very simple idea. That's it. Now, natural thing to do here is, since you've computed an upper bound, is you minimize this, right? So, and I should mention a couple of other things here. At least the theory says this: if you're able to search over all possible v's, this would be sharp, because there is a v for which this is equal to that, right? That's actually not that interesting in practice, because we can't search. You can't represent a function on R10. No one can. There's no way to really represent an arbitrary function on R10 in practice. Absolutely none, right? So, I mean, it's nice to know that if you could, you would get the exact answer. It's not, from an algorithmic point of view, or if you want the number, it's not that useful. We'll see a couple of examples of that. Okay, so let's fix a quadratic Lyapunov function candidate. This tells you that it's non-negative. And those inequalities turn into, this used to be an equal sign, now it's a less than or equal to, right? And so notice that this theme, this is a theme from 1892, that you go from a conserved quantity to a dissipated quantity. So these are very old ideas and themes. So you get something like this. Now nowadays we would look at that and say that is a set of linear matrix inequalities in P, right? Because P is a variable here, that's a matrix inequality, and I can put this P over there, and it's a matrix inequality, it's an LMI. And we would minimize this thing, that's a linear function of P. It's a quadratic function of X, but a linear function of P. And minimizing a linear function of a matrix subject to some LMIs, that's a semi-definite program. And that's something we can do. Totally effective. That's completely effective. Okay, here's the CVX source. Again, you've lost all the red, which would have been for the keywords. The keywords are in red here. But that's okay. You still see the structure of it. So that's the source code. That's the actual source code that solves this problem here. It says this has to hold, and you want to minimize that. Okay? And here's the CVX source. And the point is, it is the source code, which is executable, looks exactly like the mathematics, except in fact it's slightly clearer, because in math we can be a little bit short with things and forget to say what the variables are or something like that. So that's it. That's the problem. And the point is, so this is something that a student can put together in 2 minutes as a homework exercise, right? So this is the idea. This is quite a sophisticated method, and the coding time will be 2 minutes. Okay, I want to use this as an excuse to talk about another use, a completely non-traditional use of Lyapunov methods. Completely non-traditional, but extremely useful in practice. Extremely useful. And here it is. It's approximate worst-case simulation, right? So here, in this specific context, the question is this: how would you get a sequence that makes J large? So this is like worst-case simulation. So the question is, which one should you choose? Should you choose A1, A2, A3, and in each step? By the way, there is some sequence that gets you close to the optimum, right? So the question is, what sequence should you choose? And so the idea is this: you have found a V which proves a bound. The best bound provable with, say, a quadratic Lyapunov function, but it doesn't matter if it's quadratic or not. Then what this says is, that suggests an outstanding way to make J big. You simply greedily maximize this Lyapunov function at the next step. That's it. Okay? And what happens is, of course, when you run this, you get a lower bound on the worst case, and that means you get a gap, because you have a number you're looking for that's the worst case performance, and now you have a number below and a number above. By the way, the worst case performance, this will work infinitely better than, for example, generating the A's at random, right? Or any other method I can think of, right? This is so simple. It's amazingly simple. It's a very good way to do approximate worst case simulation, right? So I think theorists frown on this. They frown on it because they say, well, what can you prove about this? Or what can you say about this? And I think the answer is nothing, or not very much. But this is still amazingly useful, right? Because if you have a practical system and you want to know how bad could this be, here's a method that's completely effective and will very quickly get you some very bad sequences or something like that, right? So, okay. So let's look at a numerical example. It's made up completely at random. It has no meaning, but it's just to see what happens here. So it's a problem with 10 states, and it can switch between 10 dynamics matrices. Totally random data. The upper bound is something like 25. And when you do approximate worst case simulation, you get 16.2. And then you ask yourself the question, what's the true worst case number? Well, it's somewhere in it. It's bigger than this and it's less than that. And I happen to know for this problem, the worst case number is somewhere around 17. Okay? So that's the idea. And this shows you all sorts of things. It shows you that, well, with quadratic Lyapunov functions, you can't get that far. Now, by the way, I would argue, I mean, this is a pretty big gap. It's like a 30% gap. On the other hand, in a lot of cases, I would argue, first of all, these are squares, right? So if you take the square root, that's a 15% gap. That's number. And then you have to accept the following fact. Were where do quadratic cost functions come from in control? So where do you get a quadratic control? Where does Q come from and where does R come from? And the honest answer is we make them up. These are knobs we use to get what we want. So if that's what Q is, it's just a rough thing, then I would say 15% is good enough, frankly. It'd be hard to imagine somebody saying, no, that's my Q, I really believe it, it's significant to 2%. I wouldn't even believe it. So, all right. By the way, for this problem, you can easily improve the gap, and that's how I know the number is closer to 17. So if you did things like this, you consider pairs of functions and apply the exact same method, that drops it down to 18. If you look at triplets and things like that, it drops it down to 17. If you use, same thing happens if you use quartic Lyapunov function and things like that, right? So, okay. All right, we're gonna look at the second example. The second example is in stochastic control. This, by the way, takes us to the year 2012. So this is now 120 years later. But actually, what I want to argue, in fact, when you look, as I describe this, what I want to come out is the following. If Lyapunov were here, he would understand everything here. It would be completely natural. And it's his ideas. Well, maybe a few others from the 60s and 70s and 80s mixed in. But basically, it's the same thing. The same thing is happening. Okay, so we'll start. You have a nonlinear, potentially nonlinear dynamical system with driven by an input. It has a state, and it has an IID process noise here. And that's independent of x0. We're going to use a state feedback policy, so ut is mu of xt. And the stage cost function is g of x and u. And the average stage cost is this. That depends on the policy, of course. And we are looking for a policy that minimizes j mu. And by the way, that's a much more complicated problem than just an optimization problem, because it's, if anything, it's an optimization problem in infinite dimensions, because we're searching over policies, not actions, right? So this is not an optimization problem, or if it is, it's a very complicated one, because it's infinite dimensional. You're searching over policies. Okay. Oh, by the way, and the year for this would be, I don't know, 1940s or something. I don't know who would use this form, but anyway, okay. So here's the celebrated dynamic programming solution. It says find a value function, v, and a number alpha that satisfies the so-called Bellman fixed point, and that's this. The v of x plus alpha is the minimum over the allowed actions of the stage cost plus the expected value of this function v at the next step. Okay? And the expectation here is over Wt. Okay? So this is this. Now, actually here, if I add a constant to V, I just add a constant to this thing, and on the other side as well. So V is a potential. It's only defined up to a constant. I can arbitrarily add a number to V. Okay? So now, in this case, if you find such a V, then the optimal policy is this. You minimize the current stage cost plus the expected value function at the next step. And alpha, in fact, gives you the optimal stage cost. Okay? And by the way, the year for this would be, let's say 1961, I would say. Something like 1960, 1961. Okay? It could be argued to be earlier in different notation. But this is the idea. Okay, so, all right. Now you can almost guess what's going to happen. You see that equality? It's going to turn into an inequality. It's going to go from a conserved quantity to a dissipated quantity. And here's what's going to happen. Well, I'll get to that later. We'll get to that in a minute. So, let me say something about this. I should say one more thing. This is a celebrated method, right? However, it's a true solution, meaning you can actually do it only in very special cases. So here are some special cases. The state space is finite, there's a finite number of actions, in which case this is called a Markov decision problem, and you get a complete solution if the number of states is less than, well, these days, 10 million, okay, or 100 million, 10 million, let's say, right? Then this is a complete solution. The other very famous case is this. If the dynamics here, if that's linear, and that's convex quadratic, then this method becomes actionable. And the reason is this. V is going to be quadratic. And all of these calculations, expected value of a quadratic is quadratic. Okay? You add one quadratic to another, it's quadratic, and this is partial minimization. If I take a quadratic function of many variables and I optimize over some of them, the result is quadratic in the remaining ones. It's the sure complement. Okay? So the point is that convex quadratic functions play nice with Bellman methods, Bellman operator, because minimization, sum, and expectation preserve convex quadratics. And therefore, this thing actually is a fixed point for quadratic equations, and in fact, it can be solved by iteration. So you simply iterate that equation, and you will converge to a fixed point. I mean, if there's some technical conditions, but that's the idea. Okay. So, and this would be the basis of things like LQR, stochastic linear quadratic regulator, right? So that's, now we really are at 1960. Okay. But in general, this is not particularly useful, because as I said earlier, you can't represent a function on R10, much less even verify an equality or an inequality. You can't do it. It's impossible, right? Special cases quadratics. But other than that, you basically, I mean, there's a few other things you could do, but you can't, it won't work on R10. It simply will not work. Okay. This brings us to the idea of ADP, or approximate dynamic programming. It's very simple. It does this. It says, that is the form of the optimal policy if you knew V. But except in very special cases you don't know V, you cannot even represent V. No way to do it. Well, except if in 3 dimensions you can do it, because I grid 100 dimensions each way, that's 1,000,000 points, that's nothing on a model, that's nothing on my laptop, okay? So that you can do. But in R10, you can't do it. It's impossible. Okay? So the idea there is you say, well, instead of V, we'll use an approximation, and you get something called approximate dynamic programming. It looks like this. By the way, the policy is now expressed as a minimization problem. It's very interesting. It says that in every step, when you evaluate the controller or the policy, you solve an optimization problem. And in fact, that's what you're doing in LQR, except you're minimizing a quadratic function, which has an analytical solution, and an analytical solution, in fact, is a linear control policy, right? So we think of it as U equals Kx. But in fact, you're solving a quadratic minimization problem at every step. We just think of it as U equals Kx. It's a solution. All right. So this is the idea. And you choose this thing 2 ways. One is we have to be able to represent it. And the second is you want this minimization to be tractable. That generally means it's a convex problem or something like that. And you also want this thing to be close to V, right? And then you get something like the true, you get close to the true value, right? That's the idea. And now, if you have seen this before, if you haven't seen it before, I'm going to let you in on a secret. And it's actually an extremely important secret. So, and in fact, I'll first tell you a secret about the whole field of control. If you first start talking to someone from a different field about control, and they say, what do you do? And I say, well, we construct these mathematical models, and then we work out a policy that tells you what to do, and at every step you can take some actions, but it's a feedback system, your actions affect the future, and it's all very complicated and all that. And then I tell them, okay, now I'm going to tell you a secret, but don't tell anyone else. And the secret is this, discovered right around 1900, maybe in fact 1850, something like that, is that shockingly unsophisticated feedback policies do very, very well in practice, like PID. And so I think that is one of the secrets of our field, right? I mean, at least when you teach it, you should explain this. And I think it's best to just admit it, to say that you have some very complicated system with nonlinear dynamics and delay, and all sorts of other crazy stuff in it. And the idea that a PID controller should work very well often when tuned, I think is shocking. All right. So now I'll tell you a modern dirty secret 100 years later. It's this. This policy works unbelievably well. And it works well even when this thing is a terrible approximation of V. Okay? And I would say that this is the analog of PID. It's the PID secret from 1900. Here is it's the ADP secret from 2000. That these policies work well. Anyone would imagine this will work well if this was a good approximation of V. That's very intuitive. What is shocking is that this thing can be very far. It just has to get the shape of things approximately. And if it gets the shape of things right, this policy will work unbelievably well in a huge variety of problems. Okay, so that's the idea. And this means judged by simulation, right? If you run a supply chain using this, or you do finance, or you do anything else, you do control, classical electromechanical control, it will work unbelievably well. Okay, and that's judged by simulation. Now, one question there is, how suboptimal is it, right? So, I mean, you implement this controller. We have methods to implement things like this. If this is convex optimization, we can implement this very fast on a microsecond time scale these days. You have a controller running. The question is, you simulate it, it works well, but then you want to know how well is it? You know, I'm making this amount of money every day or whatever. Could I make twice as much? And so you want to bound on it. You want to know, how much better could it be? And that leads us to, guess what? Lyapunov. So, and all that's going to happen here is the following. Here, whoops, here's the Bellman equation. And surprise, surprise, the only thing that's going to happen, and it's as if it's 1892 all over again, this equality is going to become an inequality. Okay? And here it is. So here's the inequality. It's going to become this, and this is the Bellman inequality. It says that if you find V and alpha that are less than this thing, then alpha is a lower bound on J star, right? And so the obvious thing to do now is to maximize alpha subject to the Bellman inequality. By the way, this shows you. By the way, this is exactly Lyapunov's idea. It says, find me a function that satisfies something involving some inequalities. And if you find a function like that, in his case, he could say things like, I can tell you all trajectories converge to zero. This is much more sophisticated. This is a stochastic control problem, and what you're doing is you'll say that if you can find a function that satisfies this, these are Lyapunov conditions, then what we'll find is a lower bound on the achievable performance for stochastic control. That's a very strong statement, right? So that's it. By the way, it is completely useless without, in my opinion, without convex optimization. Because what convex optimization is going to do is going to turn this abstraction into something with algorithmic teeth. It's something that you can actually do. Okay. Now, when you solve this, you'll get a lower bound. And then you'll get, suppose V is quadratic. You will get a quadratic approximation of the true value function. And that will be an outstanding choice for a policy. And then this says that you can do two things. It says that a very good way to construct a controller, in fact, in my opinion, it's probably the best way to construct a controller for stochastic control, and it's this. The first thing you do is you write down a Lyapunov condition to try to get a performance bound, to find out, to get a number that you can prove no one can do this well. That's the first thing you do. Now, if someone comes along to you, like your supervisor says, what are you doing? You say, I want to get some numbers to find out how I want to show that no one can do this well. And they'll say, but we didn't pay you to do that, we paid you to make it work. And you say, just wait, right? So you come up and you find this thing but one of the side calculations is you'll end up with a V that gives you the best bound, and that goes into an ADP, and you'll get now a good control, and you'll get a bound, so you can actually say something about it. Let's look at an example, and it'll be a fun example, because this one I made up. I promise I did not change the random seed until the problem did what I wanted. I just did it, and everything's completely random, but it actually gives all the right ideas. Okay, so here it is. I have a linear dynamical system, very conventional. That's completely conventional cost. So this is stochastic LQR. We could solve this problem exactly if U were unconstrained. If U is unconstrained, this is just stochastic LQR. We solve a Riccati equation. We get the answer. Okay? But what I'm going to do here is the input actually is quantized. You can only choose k different values. That's it. I mean, k could be enormous. I don't care about that. But the point is, you can only choose a finite number of possible inputs. That's it, right? By the way, that's a rather substantial constraint, right? So the cost compared to LQR is going to go up. By the way, it could go up to plus infinity, of course, right? Because you just don't, it's impossible. In fact, if A is unstable, it will go to plus infinity, period, right? Because They'll be a state large enough from which you don't have enough control authority to ever recover, right? Okay. All right. So let's apply just Lyapunov's idea. So let's just apply his method. Well, we'll look at a quadratic Lyapunov function candidate here. A quadratic Lyapunov function candidate. And the Bellman inequality is this. That's v of x plus alpha is less than, that's the stage cost, plus the expected value of v, that's this thing transpose that, of ax plus b plus w transpose. And now watch what's going to happen. All sorts of things are going to just fall away. This thing here, the expected values over wt has zero mean. So the cross terms are zero. And the only term that this stochastic part contributes is this one. Its expected value of wt transpose p wt, that's this. And the rest is what's left otherwise. It looks like that. Okay? But this is a quadratic in x with an offset. That's a quadratic in x with an offset. It's a quadratic function. And it turns out, this is very basic. You just simply transcribe this and it looks like that. So this inequality holds for all x if and only if this one does. Right? And so now we look at this and we say, oh, that's an LMI, because this matrix is linear or affine in P and alpha, those are the variables. It's a matrix inequality, and this input set is finite, so this is just a set of these, and now I maximize alpha, and that's a semi-definite program. Okay? So, and now I can do several things about it. I could write a paper about that or something, but you can also implement it. And that's the implementation. That's the entire thing. Okay? And that runs. That's the code that I used to solve the numerical example, right? And the point about it is that it's very straightforward, right? The code, a student could write this. This could be a homework problem. And it is a homework problem, in fact, or will be, because I made it up for this talk, but next year it'll be in my course, right? So it's a homework problem. And the idea is this is doing something very, very sophisticated, and it takes a student about 5 or 10 minutes to do this. So this is actually empowering, right? To be able to do something like this in 5 minutes is empowering. Let's look at a numerical example. So a numerical example is just 10 states and 3 inputs. Oh, I should say, all of these would scale. This could be 100 states easily. And in fact, with a little bit of effort, it could be much bigger. It doesn't matter, right? These things scale. That's one very big difference between 1892 and now. In 1892, everything was done by hand. That's true all the way up until the 50s. Everything was done by hand, right? Pencil and paper. That was great for 4th order systems, 5th order systems with a single nonlinearity, fine, right? Everything. Now it scales. These things scale. They go to much larger systems. They handle all sorts of, okay. So here's the example. It's got just random data. Oh, by the way, there's only 10 input values in R3. Now, if you think about that, that is extreme quantization. Because if I only gave you, say, 3 values in each direction, that'd be 3 to 3. That'd be 27. That'd be 27 values. This is 10. So this is, I don't know what the cube root, not the cube root of 10, whatever the correct number. Yeah, the cube root of 10 is. Whatever number you get, there's about 2 values for each dimension of control. Right? It's the cube root of 10. Right? So this is extremely quantized, the system. Right? And so you'd imagine this would never even work. How could you possibly control? How could you do stochastic control with 10 possible input values in R10? By the way, R3, chosen random. Well, the LQR cost for this problem, it's about 42.5. Okay? So whatever the cost is going to be, with this extreme quantization, it's got to be more than that. It could have been plus infinity. Well, the lower bound is this, 68.1. By the way, it still could be plus infinity. This is just the lower bound. And 68.1 is a valid lower bound on infinity. Okay. But it turns out if you run the ADP controller, you get 78. Okay? So I just made it up. I mean, and I'm asserting nothing other than this was the one example I tried. I tried a few to make sure it wasn't wrong or something like that, right? So there it is. By the way, what's totally bizarre, this says that this is nearly optimal, by the way, because, you know, this is, I don't know what that is, it's 10, so it's like 14%. It's a square, you should take the square root, you're at 7%. Anybody who says that's not optimal, they have to justify their Q and R are valid within 5%. And I don't believe anybody anywhere can do that, because that's not where Q and R come from in control. So what this says is that's an optimal control. By the way, you might ask, does this have any practical uses? And my answer to that is I'm absolutely certain it does. For things like switching power supplies and things like, I can think of lots and lots of applications right away. Right. So, okay. So that's it. I'm just going to finish up with some conclusions now. So what are the ideas here? Well, the first idea is this. Lyapunov's methods, they apply to far more than just stability theory. We teach stability theory, right? But in fact, my opinion is this, that's not even particularly useful. I mean, it's interesting. It's not particularly useful, right? What's useful is the ability to actually give a number, like this decays at this rate, or this performance number is less than 12.7. That's actually useful. You say things like this. If this plane is flying at this trim condition and there's a downdraft like this, I guarantee you it will never go more than 100 meters low before returning to its set point. Okay, that is useful. Saying it's stable is not useful in any way. Okay, in my opinion. Okay, so the main point though is this. Is if you take an idea from 1892, suitably generalized, by the way, to handle things like control, bounding, performance indices, time-varying systems, uncertain systems, and if you take that, these things, and you couple them with convex optimization, you get a combination that is extremely powerful. Extremely powerful. By the way, what's also nice about it is it's extremely simple, and therefore this is teachable. Which I love the idea you can teach to undergraduates stuff that is beyond the cutting edge of research. Because if you know these two things, you can put things together. An undergraduate can put things together that are beyond the edge of current research. Right? They're incredible things. Right? What's more, it's kind of fun. For me, I find it interesting because although it's quite theoretical, I mean, a lot of it involves the theory, but it's also at the same time, it's very concrete. You get numerical answers, right? I'll tell you what you won't get. You probably won't get the respect of people who do traditional theory-oriented control. You will not get their respect. Because when you show them these things, they will say things like, oh, that's very nice. What can you prove about it? And the answer would be something like this. Like, let's go back to this example. And you'd say, well, here's the true mathematics. I'll tell you some true mathematics. That number, that's real. For this problem instance, nobody can do better. There's no policy that beats that number. Actually, the funny part is when I put on my true mathematics hat, this number is suspect because this number comes from Monte Carlo. So that number is suspect. This one is absolute. But what someone who comes from the culture of the pure theory, the pure control theory, what they will say is, oh, but this was just one example. Can you always prove it's within 15%? And the answer is, of course not. Of course you cannot. Right? So, and actually, I think it's better to just admit it and say it in the open. We can't do it. Oh, and by the way, this still is unbelievably useful. Right? This is, in my opinion, is that you're looking at the PID control of whatever the century is called. Right? So this is the PID control from the century. Right? No one ever stopped and said about PID control. You don't walk into a factory and say, what are you doing? You say, well, I'm running this process and I have a PID control. You don't ask them, oh, can you prove the performance? Of course they can't prove the performance. It's ridiculous. Right? So, all right. So I claim this is the PID control of this century. Okay. Now, what's nice about all this is a lot of this was already developed in the 90s, maybe last decade, something like that. But I think what's happened is these modern tools make it easy to do. This is now within the reach of students, of undergraduates. The gap between coming up with, I made up these examples last week. I just made up the entire thing. I typed the scripts in, in 1 minute. It took me 2 minutes to debug them. And I had it running. I didn't even look back at the papers I'd written on these things. And It was easy, it's just easy to do. So it's actually easy, it's highly teachable. And my claim is, these ideas, this should be universally taught, right? This would be a huge service, actually in control education. This would be kind of a revolution to do this, would be to throw out a lot of the classical stuff. Just throw it out. I'd keep PID, I didn't even know what, I might leave in things like Bode diagrams and things like that, root locus, just for cultural background. But the rest, I'd throw it out. And I would teach Lyapunov's ideas from 120 years ago, coupled with convex optimization. Now for references, I'm going to list some things here. These are books I've written, and I want to be very clear about it. This does not mean that I had a lot, in fact, almost anything to do with anything I've talked about today. So I want to make it very clear. These are indirect references. If you go to these books and look at the references, you will then find who actually did most of this work, a lot of this work, right? So just to make it completely clear. By the way, all of this, the way you find it, is you simply go to Google and you type in any word even close to anything I've talked about, and hopefully you will very quickly find these things. So, okay, so I think I will quit here.
Maybe 1, 2 questions before we will have coffee break, right? Do we have coffee break, Pavel? Or I made it? Okay, so question, comment? Yes, please?
From control education point of view, I would like to know your opinion.
Everyone.
You say that most of the control rows design method can be reformulated as a combination of a Lyapunov method with a combination of optimization. Of course, then when you try to explain to your student a particular robust control method, I suppose that you provide some kind of mix. You try to give the fundamental of the method in order to provide that the method can be reformulated. Because if you only provided the general framework, the student cannot understand what is the method and the relation with the general procedure that you mentioned. Is correct my assumption or not?
That is correct, right? And it's a bit bizarre, right? Because it means you would not teach. By the way, I have not done this yet, so this is just a radical proposal. You would not teach about our beloved Riccati equations. This wouldn't be there. Hamiltonians, gone. So the Riccati equation would be some historical, it'd be some historical oddity. It would be this very special case of an LMI that we could solve in the 60s through the 2000s or something. And beyond that, it would be a historical footnote. So that is the proposal. It's crazy, but that's it.
Okay. Thanks.
Other question?
One shot.
Sure.
Yes.
Of course, we absolutely agree with you, especially with the last thesis. It should be universally taught. But what about your opinion? How do students understand all these interesting things?
So my claim, so I have not taught a radical control course like this, although I intend to. But I have taught a radical convex optimization course.
Nice.
And that works really well. So that works very well because you talk about 50 different application areas. In no application area do you go into detail. But for every single application area, the students actually work real examples, numerical examples. They do machine learning, they do finance, they do control, they do signal processing. Small little things, but enough to see that it actually does something. Right? So my suspicion is, although I have taught enough to know, something like this class, this could work.
I would like to add that and remind you from biography that professor teaches at Stanford. So anyway, he has also some special students and very well prepared students. So I wanted just to make you feel more comfortable. That he works with very
It's the
selected
best
students.
solution.
Yeah, I wanted on this occasion, because Professor mentioned so many times that he teaches for a diverse group of students from different departments and so on, so on. So I'm curious whether that course that you teach for that diverse group of students is listed like cross-departmental, or is just electrical engineering course? How is it?
Okay, so it's listed now in 3 departments. So computational mathematics, I think, CS,
Okay.
computer science, and electrical engineering, but we get students from 20 departments.
Okay.
Yeah.
This is obviously an excellent idea to bring students, but you have to somehow always assume what is starting point, what is that level that we start. Anyway, other question, we will continue our discussion through those 3 days. Professor is with us, so we will discuss. Once again, thank you, please join me.